The last time we were looking at all these properties of sines and cosine functions and their superposition, and we were looking at the Euler identity. And among other things, we showed that from the Euler formula, e to the I of phi equals cosine phi plus I sine phi, we can derive this sum of angles formula, which we also looked at as being derivable as an exercise in Euclidean plane geometry. It's much simpler going in this way. So we're concerned with the sum of two angles. What is happening? Oh, it needs to be turned on. Yes. So we're concerned with the sum of two angles, x and y. So if we take e to the I times that sum, that's, of course, the product of e to the ix times e to the iy, addition rule for exponents. So on this side, we can say we have cosine of the angle plus I sine of the angle, where the angle is this sum of angles, x plus y. And on the other side, we say for e to the ix, we have this expression from the Euler formula, cosine x plus I sine, and similarly for the y part. So if we just multiply these two binomials together and then collect terms, what we end up with is this expression. So we get a new binomial in which we've got collected all of the real valued terms together and all of the imaginary valued terms together, and we have then the formula we sought. Cosine x plus y is equal to cosine x cosine y minus sine x sine y, so cos minus sine sine, and then for the mixed terms, cosine sine plus sine cosine. Fine. So here they are written in red and blue, and we deduce that we can readily get from them an expression for the square of the cosine and the square of the sine. That is, we consider the case when x and y are equal, and then we can do the same kind of thing for the mixed products, cosine, sine products, sine, cosine. Okay. Next. Oh. It's not going to listen. It doesn't have ears. Okay, so that's the geometrical proof. And then what we left off was we said, okay, we'll get to this rotation of axes stuff. It's going to become important for us when we get into considering the rotation translation searches for molecular replacement solutions of crystal structures. And this, of course, for the rotation part. And it's an important example of this use of the sum of angles formula. For the first orientation of the axes, x and y, we have the x component here is equal to r, the radius, the length of the vector, times cosine theta, y, the similar r times the sine of theta. And now we look at the coordinates in this rotated system. So we're just, if we imagine an XYZ frame, we're just rotating about the z-axis in the XY plane. And we rotate by an angle phi. Well, we rotate the axes by an angle theta, and what that does to the vector is change its argument part to the angle phi. So we've got, by construction, theta, here is theta, the rotation angle for the xy axes. That means that this angle, when we drop this perpendicular to the new x-axis, this angle is theta. When we drop the perpendicular to the new y-axis, this angle, again, is theta. So we have that x prime is equal to x times the cosine of phi plus y times the sine of phi, and so on for the y component, and the z doesn't change here. And if we rewrite this set of expressions, which comes straight away from here using the sum of angles formulae. We rewrite this as a matrix equation. Then the new coordinates are x prime, y prime, z prime. This transformation matrix in the cosine and sine terms, right? Unit term here for the z rotation, right? The z coordinate doesn't change. So this transformation matrix, just the terms from this set of equations, times the original coordinate vectors, the original coordinates x, y, z. So that's an important application of this sum of angles formula, which we spent some time playing with. And you can also consider the case where we're not rotating the axes, but we're just rotating a vector. We have this original vector in red, and so it's got r cosine alpha and sine alpha as its projected coordinate. And then in the new position of the rotated position of the vector, we rotate the vector by beta. We get then these components expressed in terms of the sum of the angles, alpha plus beta. We use that handy formula for sum of angles. We get a new pair of simultaneous equations, x prime, y prime, z prime equals x cosine beta minus y sine beta, and so on and so on. And then so we get this transformation matrix from these coefficients, cosine and sine coefficients, and we get a new transformation matrix, which is similar in form, but different from the transformation matrix for rotation of the axes. So we'll be using both of these later on. Okay, so that concludes what we wanted to do last time, or what I wanted to do last time. So this can be put away. And now we're getting into where all of this sine, cosine, and superposition business and the Euler formula was taking us to where we wanted. This is where we wanted to be, where we wanted to get. So these, we remember, are the kind of basic relations coming from Lowy and the Braggs, and then subsequently the intensity formula from Charles Darwin. Right? So these are kind of the rudimentary expressions for dealing with the X-ray diffraction patterns, positions and intensities. Positions of the reflections, angles of the reflections, and their intensities. And we had remarked on this too earlier, that this Fourier analysis was recognized as a tool to use, even before it was put to use, by Bragg the Elder in a lecture that he gave before the Royal Society. And so Bragg the Younger points out quotation from his father from 1915. Okay? So we're talking very soon after the Bragg law was discovered, very soon after the diffraction of X-rays by crystals was discovered by Lowy, Friedrich, and Knipe. Bragg the Elder foresaw that Fourier analysis, which had been around since, let's see, what was Fourier's paper was 1807. So a little more than 100 years, Fourier analysis had been around and had come to have many applications. So Fourier analysis for us is, in essence, the fundamental theorem of structural crystallography. That is, we have the structure factors in general complex value in reciprocal space, or HKL space, and we have the scattering density distribution over the unit cell, or electron density in our case, in crystal space, XYZ space, and these two are related by Fourier transformation. One is the Fourier transform of the other, and vice versa. And we express this business of saying the Fourier transform just by convention, we say the Fourier transformation of the structure factors to get the density is what we call Fourier synthesis. We synthesize the density from a set of structure factors. And going the other way, when we invert that density, reverse Fourier transform that density, we get the structure factors that we refer to as Fourier analysis. But these are just conventions. Where is the two transformations have to be of opposite sign, and the terminology, both the sign choice and the terminology, are matters of convention. But I think I'm using here probably the most widely used convention. And if I try to switch to the other one, then I'll get all debuggered up. And my eyes cross. Okay, so what Fourier had shown back in the early 19th century was that if we have a periodic function, f of x, that is, by periodic we mean that f of x is exactly equal to f at x plus 2n plus or minus 2n pi. So it's a 2 pi periodic function that we're considering here, and n can be any integer. Okay, so that function then has an expression, whatever that function is, as long as it's got this property of periodicity and at least piecewise continuity. It can be expressed as a series, and in fact, in principle, infinite series of cosine and sine terms, where these coefficients, the a's and the b's, a naught is the special case. It's equal to the integral of this function from minus pi to plus pi. So it's the integral of the function over one period. Okay? And the higher orders, the a sub n and b sub n, are similar, integrating from minus pi to plus pi, the function multiplied by cosine nx, where n is indexing the terms in this series, or the function multiplying sine nx, and each of these scaled by a factor 1 over pi. So if we know something about the form of the function, we can get the coefficients of the infinite series. If we have the infinite series, we can back transform and the result of the series summation and get the coefficients. So interestingly, when Fourier announced this idea, I think it was presented in a lecture before the French Academy in Paris. There were other, notable worthies in the history of mathematics. This was a period of a flowering of mathematics in France. So people like Lagrange, Laplace, Legendre, Malou, all thought that this formulation was a little bit sketchy. And so they didn't quite say, okay, Fourier, you're a genius and you shall be enshrined in the Hall of Heroes. Not immediately, but later in Germany, Dirichlet and Riemann went through a thorough analysis, gave a more precise and detailed derivation of the Fourier series result, and it is now universally accepted and widely applied. So there's the guy, Fourier. Here's the passage in his writing, which is the central part of the story. He's looking at this function phi of y, okay, and he's able to express it as this cosine series. Right? And he shows then how to get these coefficients of the series, a prime, a double prime, by means of multiplying on both sides by this cosine, this particular cosine. We should go on to the next one where it's a little clearer. Only slightly clearer. But anyhow, multiply on both sides by this cosine term. And what happens then is, for all except the case when I prime in his notation, I prime is equal to I, so except for that one case, all the other terms in the series drop away, and we can evaluate the coefficient. There it's written a little more clearly and in kind of conventional notation. So this cosine-cosine product will be equal to 0 if n is not equal to n prime. Okay? But if they are equal n prime, then this goes to unity, this particular cosine-cosine definite integral. So going from integrating over y from -1 to +1, which is what this is expressing, that's the same, since the variable that he chose to talk about was pi y, that's the same as integrating from -pi to +pi, which is more conventional way of thinking about it now in these times. That's the same slide in black and white and black instead of black and white. Okay, so we look a little bit more closely now at the Fourier series expansion of some 2 pi periodic function. Some function f for which f at x is equal to f at x plus or minus 2n pi for all real values of x. So that trigonometric series that we take straight from Fourier's first expression of the Fourier series, okay? We have this first a naught coefficient is given by integrating the function minus pi to pi, integrating over x. Here, the other higher order coefficients, a1 and so on, and b1 and so on, are given by multiplying the function by, in the one case, cosine nx. So we've got this harmonic series of cosines. Cosine of x, cosine 2x, cosine 3x, and so on, as we go out this series, summing over n, in principle from 1 to infinity. And similarly, for the b coefficients, a sine series, S-I-N-E series, obtained by the same kind of integration. And here we immediately apply our old and dear friend, the Euler relationship, in terms of which we can write out the cosine as 1/2 the sum of e to the I phi and e to the minus I phi, and we can write out the sine as 1/2 of I times the difference between the two, e to the I phi minus e to the minus I phi. So we can re-express the trigonometric infinite series in terms of a complex exponential infinite series. Now you may not think that that's much of a simplification, but in fact it turns out to be. So we write out the Fourier series in terms of e to the I phi. So now we can collect terms, right? So we have the a coefficients and the b coefficients. So if we collect terms that are the same in e to the I n x or e to the minus I n x, so now we have a recognizably complex number here, a sub n minus ib sub n, a sub n plus ib sub n. And what that means is these two coefficients, a plus bi form, one is the complex conjugate of the other. We get the complex conjugate by simply reversing the sign of all of the I terms. Okay? So this bit becomes, we can call it a coefficient c sub n. Right? Simplify the notation a bit. And this part we can say is a complex conjugate of that, because these two terms are complex conjugate of each other. This bit we treat as the complex conjugate of this bit over here. So now the series can be written so that it looks simpler. Nothing is changing here. It's just a matter of using the underlying algebraic and trigonometric relationship, the Euler relation. So we have now expressed the series in terms of these coefficients c 0, c sub negative n, and c sub n. Right? So combining all those terms, we can say instead of it being a series, a sum over n equals 1 to infinity, we can say, okay, this is a series in which each term has this same form, but we're summing now from n equal minus infinity to plus infinity. Sir?
Where do the expressions for cosine phi and sine phi come from?
You mean under the top box?
Yes.
Okay, so if you have the Euler relationship here, if you write underneath it e to the minus I phi, well then you get cosine phi minus I sine phi. All right? Yep. So you can sum those equations because the sine terms have opposite algebraic signs. They go away, so you get 2 cosine phi. Yep. Right? That's why it has to be a half. And you're summing, if you sum those 2 equations, e to the I phi and e to the minus I phi. And you do the same thing to get the sine terms. Okay? So this is just another way to define the sine and cosine functions. And notice here, you may not immediately think this way, because you're not dealing with complex numbers every day, but the quantity 1 over I is equal to the negative of I. And you can see that by saying, okay, I'll take 1 over I, I'll multiply numerator and denominator by I, and I get I over I squared. But I squared is minus 1. So minus I. 1 over I becomes negative I, but we've multiplied by a half. So this is the handiness of all of that stuff we were talking about on and on last time. Okay, so we have the trigonometric series, or equivalently, the complex exponential series. Now we can generalize a little bit. Things get a little bit more messy in the notation. If we don't want to restrict ourselves to a function whose period is 2 pi, we can have a function with an arbitrary period, call it L for a length, say. So that f of x is equal to f of x plus or minus n times L for all x, for all real x. So we make those substitutions. So what was, if we go back one, so what was simply cosine nx and sine nx in this expression, the trigonometric expression, they become cosine 2 pi nx over L. So we have to scale this periodicity L because we know that the cosine function and sine functions are 2 pi periodic. So we can introduce an arbitrary period in this way, then following through the same expressions, the same form of expressions as we had in the top box on the previous slide. We get these new expressions in terms of L for the A and B coefficients. Do the same trick with the complex exponentials using the Euler formula. Then the Fourier series becomes the sum from n equal 1 to infinity of these terms, which look hairier just because we've got this hairier expression for the sine and cosine arguments. Do that same business of combining terms and the A and B terms that have the same exponential 2 pi I nx over L minus 2 pi I and x over L. So we get this complex coefficient, a sub n minus ib sub n, a sub n plus ib sub n. We say, okay, let's call those guys, these complex numbers, let's represent them, give them a new symbol c. So c is complex. So the one with the sum terms here becomes c sub n, and this guy with the a sub n minus ib sub n is the complex conjugate of c. Okay, so these we get the c and c star coefficients. So the complex exponential expression of the infinite series from 1 to infinity becomes the simplified notation, at least notationally simplified sum from minus infinity to plus infinity, where we now have these complex valued coefficients C. And they're obtained in the same way as for the A and B coefficients. We multiply the function by this exponential kernel, and then integrate over one period. Integrate from 0 to L, or from minus L over minus a half L to a plus a half L. Okay. So that reviews some of our Euler relationship algebra and applies it to this infinite series, the Fourier series. So now we want to talk about a property of the sine and cosine functions. That was the property that Fourier relied upon when he said, okay, we get the coefficients by multiplying on each side by cosine of whatever that argument was, and that meant that all of the terms on the infinite series side dropped out except the one where you had I equal I prime. And that's not the imaginary unit. Fourier chose this as just the symbol for the index. So what that means is that he was able to use the fact that if we integrate the product of cosine of mx times the cosine of nx, where m and n are integers, but not equal to 0. So plus or minus 1, plus or minus 2, and so on. And similarly, if we do that with a product of the sine functions, sine mx times sine nx, do that integration from minus pi to pi, then that goes to 0 if m and n are not equal, but it survives and goes to pi if and only if m equals n. And in the case of mixed products, cosine, sine, sine, cosine, those for all m and n integrate to 0. And we'll see how that happens, I think, a slide or two down the road. So this business of orthogonality of the sine and cosine functions is what allows us to evaluate the coefficients, a sub n equal 1, 2, 3, and so on, by multiplying on both sides by the coefficient, the term with the coefficient we're seeking. All the other terms go away except the one surviving. So this property of orthogonality is one half of the story of properties of orthonormality of functions. So if we consider two functions these don't have to be periodic functions now. This is a more general property of functions. If these two functions, if we have them defined on some interval of x from between a and b, then if we do that integral of the product of those functions, like we were doing product here, sine, sine, cosine, cosine, and so on, and integrate over the range of that interval, then we get, again, the case where that integrates to 0 if f of x does not equal g of x. So anywhere in that interval where the two functions evaluate to different values, then this integral will vanish. But at the one point where f of x, the one point x at which f of x equals g of x, then this integrates to 1. This is the property of orthonormality for this pair of functions, a quite general pair of functions, as long as they're integrable over some defined interval. And the notation we use here on the right-hand side in these expressions is the so-called Kronecker delta, Kronecker, a German mathematician. And so this delta ij, or delta mn, or delta fn simply says, okay, if I equals j, or m equals n, or f equals g, then that evaluates to unity when these are equal. Otherwise, it evaluates to 0. So that's a handy notation that gets used very often in analysis of this kind. Okay, so that's the property. Now, how do we show that that is a valid result? I think that's okay. So around comes our old friend again, the sum of angles formula. So if we consider cosine x plus y and cosine x minus y, we have these expressions which we would just write down. So cosine x plus or minus y is equal to this expression minus or plus. And then we can solve that pair of equations to express the sum of the two terms, cosine x plus y plus. So we just add these equations, and we get then what survives is twice the product cos-cos. Right? And the sign products, sine, go away because they're of opposite algebraic sign. And then similarly, for the difference, we get the twice the product of the two sine functions, sine x, sine y, because when we subtract these guys, then the cosine factors are of opposite sign, and they go away. So now we want to consider these orthogonality integrals. Okay, for the cosine, we want to know about cosine mx times cosine nx. If we integrate that over one period, what do we get? Well, we can say, using these expressions, we can just half these guys, factor out 2. So we get half the integral of cosine m plus nx and cosine m minus nx. We're just plugging in here, okay, into this expression. Well, what do we know about that? We talked about the integrals of the trigonometric functions. So that over a period, over any one period, the cosine and sine functions have the property that they are as often positive as negative. So they integrate over one period, the integral of the cosine function is 0. Similarly, the integral of the sine function over one integral is 0. I see that this should be sine, of course. If we're dealing with the sine-sine product, then we should be talking about the sine functions in here. Here are the cosine-cosine product, and we're talking about the sum of those two kinds of cosines. Sorry about that. I'll correct it before I put them on the FTP side. But in the same way, they will evaluate to 0 if m and n are not equal. Well, what do they evaluate to if m and n are equal? Well, in this case, this integral over cosine m plus n would integrate to 0, but the second part of it, the integral, these guys would integrate to 0, but the second part of it is to sum up all those little dx's over that integral minus pi to pi. So if we integrate just over the x variable, dx, from minus pi to pi, we get a half the value of x evaluated over that range, minus pi to negative pi to positive pi. Well, that comes down to pi. So if m equals n, the integral we seek evaluates to pi. So we write it as pi times Kronecker delta mn. If m equals n, fine. Then the Kronecker delta is unity, we get pi. If m is not equal to n, then the Kronecker delta is 0, and this evaluates to 0. So in the same, exactly analogous way here, if I had remembered to put in the sine function. That's what happens when you just copy and paste without thinking. Just changing the color was all that was on my mind then, not changing the functions. Okay, and then similarly, if we consider the sine of the sum of angles, the sine of the difference of angles, evaluate these guys in just the same way in order to get at the integral of the sine-cosine products, then we see that we get an integral of the sine function, sine of m plus nx, right? But again, as often negative as positive, so this piece of the integral evaluates to 0. And similarly here, the sine of whatever this argument might be, m minus n times x, that integrates to 0 for the same reason. The sine function over a period integrates to 0. Oh, I should have gone with this slide. This also has the same misprint. I just blew it up to make it a little bit easier to see. Well, anyhow, when you get the slides, you can just step through these steps and see how these integrations give us the orthogonality condition for the sine and cosine functions. And that's the mixed terms. So we got at all this by means of our old friend, the Euler formula, which implies the beautiful Euler identity. So we kind of enshrine Leonhard Euler, a handsome devil, wasn't he? Yeah. Quite a beaker there. Okay, and there's his famous formula. He was not the only one to think of this formula. He was the one, however, who made it explicit and capitalized on its usefulness in his further mathematical work. But there were others working at the time, and similarly, there's a formula just like this where we say n phi and sine n phi and consider e to the I n phi. That was a French mathematician, Dumas, who actually came upon that result somewhat before Euler published his result. I don't know, Euler probably had it in mind at the time. Okay. Euler did other things too, interestingly. He considered the Platonic solids, okay, tetrahedron, cube, octahedron, pentagonal, dodecahedron, and icosahedron. So these are the only 5 solids that can have congruent faces, regular polygon congruent faces. So equilateral triangles, square, equilateral triangle, regular pentagon, again, equilateral triangles. So what he discovered was that if we consider those 5 special objects, the Platonic solids, that you can derive this result. E minus k plus f equals 2. So that's vertices minus edges plus faces equals 2. That's the number of faces, the number of edges, the number of vertices. So this beautiful little geometric condition applying to an effect, and in effect defining the Platonic solids, which of course go back to Greeks, classical Greeks. But interestingly, this form, E minus k plus f equal 2, is the same form of this expression, which is the Gibbs phase rule. The phase rule has to do with, say, different solid, liquid, vapor phase of, for example, water. There are these phase rules that at any point in pressure, temperature, space, this has to be true of the various phases, the solid, liquid. So the number of degrees of freedom is equal to the number, minus the number of components, plus the number of phases, must evaluate to 2. This is a cornerstone piece in materials science, physical chemistry, theory of solutions, protein crystallization. from solution. Or even from the vapor. If you could sublime your protein and crystallize it from the vapor, that's fine too. So here's giving credit to Gibbs, an American physicist at Harvard. Here's an example of a phase diagram a simple phase diagram for water. So this pressure temperature range enclosed in this kind of white area, that's the regions of pressure and temperature where we have ice. In this blue area, we would have, under those conditions of pressure and temperature, liquid water, and in the yellow area, we would have water vapor. Just a beautiful symmetry between this abstract solid geometry and this practically important physical chemistry. Okay, how are we doing on time? Well, we're okay. Right? We go till 11. Yeah, we have another roughly half hour, 20 minutes at least. Okay, so what about applying all of this Fourier series stuff and Fourier integral stuff to functions that are not periodic? That wasn't something that Fourier himself worried about at the time, back in the beginning of the early 19th century. Well, one way to approach it is to think of an aperiodic function as being periodic, but with an infinite period. Okay, so we just stretch out and make these long periods. Here's the function of interest, which we have defined on this integral a to b. A is a negative real number here, b is positive. And then the period that we allow for this function is from minus L to plus L, so that this guy is equal to this guy one period away. It's also equal to this one period in the other direction. Right? But we can now consider, let's let L get longer and longer, get these little confined function pieces to get further and further apart. So symbolically, we write this down as saying, okay, the function we're considering now is this periodic function with period L, and we define this function such that for for x less than a, okay, but greater than L over 2, so x values in this area between minus L over 2 and a, then we say the function is 0. Okay, the function evaluates to 0 here along that range in x. And similarly, on the other side, in this little range from b to plus a half L, it evaluates, the function has a value of 0. And in that special place between, in the range a to b, g of x, whatever the equation of this funny little two-humped curve, that's the function g of x. So in this little range, it's a function g of x. And then we say, okay, here's the periodicity condition. And we say that we're considering cases where the period is much greater than the range of non-zero values for the function. We're letting the bits of the function, this is repetition of this little finite function g of x, be repeated at intervals of L. And we say that what is this function g that we're trying to seek? Well, it's equal to the limit as L goes to infinity of this function, periodic with period L. So how do we evaluate that? Well, we can write this down now. This part of it we're thinking of as a periodic function, but with long period. We write down the Fourier series, and we write it in the complex exponential because it's an economical notation, right? So we have f sub L of x is an infinite sum from minus infinity to plus infinity of these coefficients multiplying the function exponential minus 2 pi I and x over L. And those coefficients are obtained by, at each value of n, taking the value of the function f, multiplying it by the conjugate. See, this is e to the minus 2 pi I. This is e to the plus 2 pi I here. Right? So we can multiply that conjugate times the function f sub L of x, integrate that over one period. So we can get these coefficient, complex exponential coefficient expression for the Fourier series. So we make those substitutions, okay, in our expression for f of x over the period L. It's an infinite series again with this long period L, but still, we're still considering a finite but long period. And we do a little bit of playing with definition of variables. So we simplify the look of the expressions by saying, okay, let's call this quantity n over L, which appears all the time here, n over L, and x and u over L. So let's call that, give that a symbol h, h sub n. Right? And that implies that the difference between adjacent values, that is h sub n and h sub n plus 1, that difference is equal to 1 over L, just by definition of what we mean by h. So we make those substitutions. We put this delta h business here as multiplying this integral from over one period of the f function, and then again multiplied on the other side by exponential 2 pi I h x. So if we call this whole quantity in square brackets here, label that as big F, you see we're getting at electron densities and structure factors, even for a non-periodic structure. For example, this could be the electron density distribution for an isolated molecule, and this would be structure factor at some place in its Fourier transform, its scattering transform at position h. And we're keeping this all in mind as one-dimensional for now. Yes, sir?
What's the definition of an aperiodic signal?
That means it means that what we're trying to get at is just this isolated, we just want to consider this function in isolation. Right? And we start out by saying, well, we know if it were periodic, if it repeated, we know how to express it as a Fourier series. And by using the Fourier series approach, but now letting the period get longer and longer, indeed without limit, okay? Going through all of these steps, we end up, as the period gets longer, that means that there's a delta h is getting smaller. So we're considering the limit of a sum, and the limit of a sum is an integral. Or put it the other way around, the integral is the limit of a sum, okay, over all values of the variable h or x, whatever. So here we go. We have now we have the form that for a function, even if it's a finite isolated function f of x, we have this expression from this Fourier integral, right? That f of x then is the Fourier transform of this transformed function that we've deduced, and conversely, the Fourier transform function is the inverse Fourier transform of the function f, little f. Okay? Again, notice the rules about Fourier transformation. So now we're not talking about infinite series anymore. We're talking about integrals. And if we know the big F and little f functions in some analytical form, we can carry out an integration. And even if we only know them in numerical form, say as a big table of f values versus h, but little steps of h and so on, we can do a numerical integration. So here we're down to what we want in Fourier analysis of either molecular or crystal electron density. So the electron density is given by the Fourier series, Fourier integral over the structure factors. The structure factor is given by the Fourier inversion, Fourier integral over the density term. Now, of course, I was clever enough to write it out in bigger type and in smaller pieces, and it would have been much easier talking our way through this if it were possible to read it more clearly. So this is just the first half of what was on the last slide, and that's the second half of what was on the last slide. But we come down to this desired result. We now have the Fourier transform integral derived from the Fourier series expression for a periodic function with infinite period. Okay, and so this is just a little summary of what was on the preceding slide. Getting from the Fourier series, an infinite series summation, to Fourier transforms, the integrals. Okay? And these are the steps that we took, just to kind of summarize. Okay, so we may be getting, no, it's only 11. Okay. It's just that I'm getting hoarse. It's a lot of talking. On the other hand, for you, it's a lot of listening. I don't know which is the more difficult part. Okay, so a point to be made about all of what we've just seen happen about the development of Fourier series. If we're considering now back again the series, the infinite series representation of a periodic function, here in blue, okay? This rho of x, y, z, or in one dimension rho of x, or in general f of x. The Fourier coefficients, here in red, c sub n f h 0, 0, this is structure factors along one direction, axis in the reciprocal space, okay? And here, the three-dimensional electron density, and here, in red, the crystal structure factor, which we get by Fourier inversion, inverse Fourier transformation of the electron density function. So the point is that in the Fourier series representation, the coefficients of each of these infinitely many terms are Fourier transforms of the function we're seeking. So for each n value, we have an integral over the period from minus, let's see, here we've called the period t rather than L. I don't know why I did that. Maybe because I made this slide earlier. But in any event, the period here is t. Right? And so we take this imaginary exponential function, e to the minus 2 pi I nx over t, and we consider its complex conjugate, e to the plus 2 pi I nx over t. Multiply that by the function itself, do the integration over one period, and we get the coefficient for the nth term, whatever n here is. We may end class a little early because I'm getting out of, I see I'm nearly out of juice. Both the slide pointer and I. Okay, so here we have the series representation. Here we have the Fourier transform from that series. And here's the one that we use in our actual work of crystal structure analysis. If we can get those, we can get the full set of structure factors in principle from negative infinity to positive infinity in each of HKL, but of course we only get a finite sampling of those because as HK and L get large, absolute sense large, either getting up in large positive values or large negative values, well, then the intensities that we can measure are falling off and become indistinguishable from background. So we have a finite sample of this, in principle, infinite reciprocal lattice. Why did I start out to say that? I don't remember. But anyhow, we evaluate from our set of, by summing over our set of structure factors, each one multiplied by its, complex exponential kernel. Here we're putting the negative sign in the kernel, e to the minus 2 pi I, hx plus ky plus lt. And then conversely, when we invert the density to get structure factors, the kernel is e to the positive 2 pi I, hx plus ky plus lt. And as I said, these terms, they must be of opposite algebraic sign, and it's a convention whether you choose to put the negative sign here or here, but you've got to have them of. The theory works out in either case if you observe the convention with negative in the exponent for the density. That's the way I kind of keep it in my own thinking. We think of the electron density distribution as being a distribution of negative charged particles, or probability distribution of negative charge. So I put the negative sign in this one. Okay, and we emphasize, I think we made this point last time, it bears repeating, that each and every value of the function, in our case this function, rho of x, y, z, each single value for each individual triple x, y, z depends on the whole set, this in principle infinite triple sum, depends on the whole set of Fourier coefficients, in our case structure factors. And each and every single value of one of the structure factors corresponding to one of the intensities of a reciprocal lattice point, each and every one of those is dependent on the whole of the distribution. So any error in our electron density distribution, so for example, missing atoms, or atoms, some atoms in the wrong place, then that's going to affect the structure factor that is gotten by inversion of that density. Similarly, if we've got error in the measurement of our structure factors, actually the magnitude of the structure factors, then it's going to have an effect on each and every point in that three-dimensional electron density distribution. Okay, this is just reviews the way people use these two conventions of forward and reverse Fourier transformation to talk about what's going on. So it's a question of terminology applied to Fourier transformation. So here's our fundamental theorem of structural crystallography. The structure factors by Fourier transformation give us the density, vice versa. By Fourier inversion of the density, we get the structure factors. And there are the explicit instructions. How do we do the Fourier transformation of this density to get this density? Well, we have this set of structure factors, okay? And it's a large set, not infinite, but large. So we sum over that whole set of structure factors, each one multiplied by this so-called kernel, complex exponential kernel. And similarly, to get the structure factor from the three-dimensional, or n-dimensional, in this case one-dimensional, to simplify things, density distribution, we take that density distribution value, multiply it by the complex exponential kernel, and then sum, and then integrate. That's the formula for doing a Fourier transformation. Multiply by the kernel with the appropriate sign in the exponent, then sum over all of the variables in whichever space you're working in, over the H space or the X space. So we write it here as an integral, assuming continuous functions f and x. But here we write it as a discrete sum, because we have only selected values of f. Right? And then each one has to be multiplied by this little interval in the h space. Similarly, we do this here, each one multiplied by the little interval in the x space. And when those intervals get vanishingly small, the limit in which delta h goes to 0 and delta x goes to 0, those are the integrals. So we talk about forward and reverse Fourier transforms. When we talk about f, the inverse transform, that is a script f to the power minus 1, we've got the positive complex exponential exponent. Okay, so going through all of this is a way to either fix these ideas in your head or completely confuse yourself. It worked for me because I'm the one who wrote it down, but I didn't have to try to memorize it. On the other hand, it may not be useful to have this table of terminology if you just sit down and memorize it. The thing would be to be able to reproduce it in a sketch on paper. So this is a look at generalization about Fourier transformation that physicists and engineers are happy with. It's a beautiful thing in the eyes of an electrical engineer, for example. It isn't all that helpful to us because it's more general than our interest in structure factors and electron densities. But there is this complementarity of, well, we've certainly looked at the complementarity of Fourier series and Fourier transform integrals, right? Here, infinite series, here, either analytical or numerical sums, integrals. And you can be talking about so-called discrete Fourier series or continuous ones. Well, in our case, what's discrete is the sum over HKL. We have those integer terms and not half-integer terms in between. So that's a discrete Fourier series to compute the density from FHKLs. On the other hand, if we're trying to get the values for FHKL, we have this continuous function, rho of x, y, z, and so that would be a continuous Fourier transform. In fact, as we shall see probably next time, we are always doing this, or the computers who do this for us are always working with discrete Fourier transformation because they're digital computers. There were, in fact, some interesting examples of analog computers to do Fourier summations. And this was before digital computers were so powerful and so widely available and so cheap. So there was a guy, a mineralogist crystallographer, a wonderful guy by the name of Dan McLaughlin. When I met him, I was a graduate student, I think a beginning graduate student in crystallography at Ohio University in Athens, Ohio. And my classmate and I and our PhD professor drove on up to Columbus to find Dan McLaughlin in the mineralogy department. And he had this great device where he could have a sandbox and set up a shaking mechanism so that he could get a Fourier map of a density. So just one section of it or a projection of it, so he could build up these little sand hills in his box, and so by that means do a kind of analog Fourier summation. Beautiful thing to see. Practically not very useful, but then the next step in the analog direction, there was a crystallographer at either Florida or Alabama, now I've forgotten, by the name of Ray Popinski. Both McLaughlin and Popinski have gone to their eternal reward. But Popinski worked with oscilloscopes, or giant cathode ray tubes, televisions, and he devised electronic circuits where he could tune them to get a Fourier, a contour map of an electron density, build a Fourier synthesis using then conventional electronics, not digital electronics. Transistors were still quite new things and only useful for those small radios that you took to the beach with. Okay. That means that the battery is dead and the class is over.